Hello and welcome back to the November 2025 IB Exams walkthrough. This is TZ3. If you're looking for the rest of the videos, it is in the playlist that is right there. But we're just going to keep on going with this 1A for HL, although there are some SL questions in common. Anyways, and so we are going to be looking at this number 6, and number 6 is going to be testing your knowledge of both Lewis structures, electron domain geometry, and molecular geometry. And so this is actually going to be an HL only question because this relies on sulfur, which has the ability to expand its octet because, where am I? Looking at our data booklet, sulfur is, it is past our group 2, so it's past neon, so it's in that group. It's past period 2, and so it's in period 3, which means it has the ability to expand its octet. It has its ability to access those d electrons in the n=3 energy level, okay? And so in terms of Lewis structures, if you have probably seen the typical way of thinking about it in terms of counting your number of valence electrons and then just messing around until it works. No, here's my thoughts. Formal charge. Even if you're SL, freaking, not gonna lie, formal charge. Formal charge. Because unless you're explicitly being asked about formal charge, or you are dealing with an ion, everything's going to be neutral, which means that every single atom tends to form the same types of bonds and same types of structures, okay? And so formal charge, if you have forgotten, is formal charge, oh crap, there we go, formal charge is going to be equal to the number of valence electrons minus the number of lines, so bonds, minus the number of dots. Okay, and so you want essentially your number of lines and your number of dots to be equal to the number of valence electrons in order for it to be 0. Okay, and so you can tell the number of valence electrons by the periodic table. And so obviously looking at SOCl2, sulfur is going to be your central atom. So you're going to have sulfur in the middle. Cool. So now oxygen. And you're like, okay, oxygen is going to be single bonded, double bonded. Well, oxygen is in this group 16. And so oxygen wants 6 things. It wants a combination of dots and lines that adds up to 6 in order to be neutral. And so mathematically, the only really way that works out is to either be, so it's either going to be double bonded to something with then 2 lone pairs, or it's going to be 2 single bonds to 2 things, so like water, with once again those 2 lone pairs. Those are really the only way that you're going to get 6, okay, without violating the octet rule. Which oxygen, because it is not in group period 3 or higher, it does not have the ability to expand its octet. And so because this oxygen is only bonded to sulfur, it has to be double bonded there, 2 lone pairs. Wow. Chlorine is in that group. It's a halogen, group 17. And so it wants 7 things. Mathematically, the only way to get to 7 with dots and lines, with dots always have to be in pairs of 2, is to be, and this for any halogen, halogens always look like single bond, 3 lone pairs. Don't even gotta think about it. So with our sulfur, we're gonna have our Cl, boop, and then our Cl, boop. Okay, and so I'm drawing crosses, by the way, just because they're easier to see from afar. Dots are kind of hard to make look bigger. Okay, and so what we're looking at this now is we have our oxygen, chlorine, all of those are neutral, except we now need to look at our sulfur. Sulfur is in the same group as oxygen, so it wants 6. Right now it has 4 lines, so it has 4. And so to get to 6 is you have to have a lone pair of electrons. And remember, your English violates the octet rule. Sulfur can do that. Sulfur loves to do that. It's its favorite activity. Okay, and so this is going to be our Lewis structure for SOCl2. And so now we need to count our number of electron domains. And so our number of electron domains, I'm going to go in, I don't know, this color. So we have 1 domain, 2 domain, 3 domain, and then 4 domains. And so 4 electron domains is going to be tetrahedral. Okay, and so right away that gives us in between C and D being eliminated. So now we're in between A and B. And so our molecular geometry, if we have 3 bonding pairs, bonding domains, there we go, 3 bonding domains and 1 non-bonding domain. And so that is going to mean that we have it being trigonal pyramidal. But you can also imagine this because you essentially have it as like tetrahedral. This is hard to show. 109.5 degrees, right? And you have it as kind of looking like this. However, this, what's it called? Get highlighted. this lone pair of electrons is going to be having some extra repulsion to where it ends up looking like a pyramid. Okay, so therefore it's going to be trigonal pyramidal. Okay, also just process of elimination as well. It's not tetrahedral. If it was tetrahedral, that would mean that it had 4 bonding domains only, and so that our only other option is trigonal pyramidal. Okay, so that gives us B for number 6. So continuing with this number 7, we're going to look at which molecule is the most polar. And so whenever we're looking at polarity, there's both the polarity of the bonds and the polarity of the molecule. And so if you draw the Lewis structure for each of these, which you have to, can't just skip that. If you have no lone pairs on a central atom, it's going to be nonpolar overall because your dipoles are going to cancel out regardless of the polarity of your bonds. However, if you have a lone pair of electrons on your central atom, that means it's going to be polar. Okay, and so CF4, I'm not going to draw the fluorine lone pairs. You get the point. Carbon wants 4 things, 4 bonds. Fluorine wants 1 bond and 3 lone pairs of electrons to make 7 formal charge added again. So CF4 is you're not going to have any polarity because all 4 of your dipoles are going to cancel each other out because there's no lone pairs of electrons on carbon. So A, no. B, CO2, carbon wants 4 things. Oxygen wants 2 bonds. Still, wow, once again, no lone pairs of electrons on carbon, not polar. Wow. C and D are both the same thing, but slightly different. So C is you have your N, Br, Br, Br. And my cat's meowing in the background. Boop. And then nitrogen wants 5 things, because that's 5 valence electrons, so it's going to have 3 lines, 2 dots. Woo! Same thing for if it was just H. So it would be N, H, H, H. Boom. Okay. And so now these are the same thing. They're both going to end up being polar. However, what does matter here now is the dipole. And so that's going to be based on the electronegativity difference between the 2 atoms. So you're going to see which one, the bromine or hydrogen, has the highest difference. So you're going to go over to your data booklet. I'm going to go, wow. Or also you could just use your periodic trends now that I'm thinking about it. But we're just going to go look at our data booklet anyways, because we're here anyways. So we have nitrogen with our electronegativity of 3, bromine also 3. Wow, so that would be non-polar bonds. And meanwhile, with hydrogen, is you have 2.2. And so that means we would have a little bit of polarity in those bonds. Therefore, NH3 or ammonia is going to be our most polar molecule. Okay, and so moving on to this number 8, it's about which allotropes of carbon are electrical conductors. And so you could just have this memorized, or you could think this through a little bit and visualize these. So this is electrical conductivity is going to be based on whether or not you have any mobile electrons. If you have any electrons that can be moving around, okay, and so if they're all stuck in a lattice, they can't be doing that. If they're all in bonds, right, they can't really be doing that. They're not delocalized. And so with graphite is essentially like you have those sheets of your carbons that are all attached to each other, but the way that the carbons are bonded to each other is they are sp2 hybridized. Okay, and so you have 1 carbon that is attached to 3 other carbons. Okay, meanwhile, that's the same thing for graphene. Graphene is the same thing as graphite. Graphite's a bunch of sheets on top of each other. Meanwhile, graphene is just one of those sheets. Okay, and so graphene is also going to be your sp2 hybridized carbons. Meanwhile, diamond is all in a tetrahedral structure. Very hard, all of that. And so diamond is they're all sp3 carbons. Okay, in terms of their hybridization. And so with graphite and graphene, like sp3, all of the electrons are in these hybridized orbitals. So there's no delocalized electrons because they're all in these hybridized orbitals, right? Meanwhile, with graphite and graphene, so since you have sp2 carbon, that means that you have 1 electron that exists in the p orbital that is unhybridized. So you have sp2 hybridized orbitals, and then you have this unhybridized p orbital. And that's where 1 electron goes, and it is delocalized. And so p orbital allows for pi electrons to be delocalized, and thus for it to conduct electricity. And so that is why 1 and 3 are correct, but not 2. And so that makes this B for number 8. Meanwhile, for this number 9, we're on this same trend of hybridization of each of these circled atoms. So hybridization is just based on the number of electron domains that you have. And so if you have, for instance, 2 electron domains, then it's going to be sp hybridized. If you have 3 electron domains, then it's going to be sp2 hybridized. If you have 4 electron domains, then it's going to be sp3 hybridized. Okay, and so one thing that's important to note, and that a lot of students fall for, is that this is essentially a structural formula. This is not a Lewis structure because there are no lone pairs shown. And that's the trick. They want you to not realize that there's lone pairs here, but there are. You have to draw them out. Okay, so for instance, this oxygen that is right there, that guy is going to have, because it needs to be neutral, there's no charge on it, it has 2 lines. Therefore, so to have 6 valence electrons, it needs to have 4 electrons. And so if we're looking at our electron domains, we have 1, 2, 3. So we have 3 domains. That means that it's sp2 hybridized. Meanwhile, with this oxygen here, number 3, is we have 1 bond, 2 bonds. Once again, it still just needs 2 lone pairs of electrons. Wow. And so this has 1 domain, 2 domain, 3 domain, and that OH bond is also a domain. Okay, so this has 4 electron domains, so it's going to be sp3 hybridized. This carbon down here, number 1, is it has 4 bonds. It has 4 valence electrons, so that's cool. Doesn't need any lone pairs. And so it's going to have 1 domain, 2, 3 domains. Therefore, it is going to be sp2 hybridized as well. So 1 is going to be sp2, so that gets us in between C and D. Meanwhile, our 2 is going to be sp2 as well, and so that still keeps us between C and D. And meanwhile, 3, we're going to have sp3, which then does allow us to have D as our final answer for that number 9. Okay, moving on to this number 10. This is a classic bonding question where you are asked about these properties and you're expected to know whether it is like ionic bonding, covalent network, or metallic bonding. Okay, and so the kind of properties that we're given this first one of good conductor of heat and electricity in solid and liquid states. And so immediately when I'm looking at this is I'm thinking, okay, good conductor of heat in the solid state. And so for it to conduct electricity, it has to have mobile charged species. So it has to have some sort of electrons that can move, something like that, okay? And so in ionic bonding, your ions can move in the liquid form because they are out of the lattice. However, in the solid form, they're stuck in the lattice, so they cannot conduct electricity in the solid form. And so ionic, I'm going to be like, no, we're taking that out because no solid electricity. Okay? Meanwhile, we also can look at covalent network structures. Those are things that, like above in this number 8, where we had graphite, diamond, graphene, all of those were covalent network structures. Okay. And so other than graphite and graphene, those are the exceptions. Other than those two, they don't really conduct electricity because they do not have delocalized electrons. Other than graphite and graphene, those two serve as exceptions, not the standard. Okay. And so covalent network structures also not some electricity. So that leaves us with covalent molecular and metallic bonding. Okay, and so covalent molecular structures, these are literally just like any molecule that has covalent bonding, right? And so if we're looking at all of our types of bonding, these are going to be the ones that have the lowest melting points, boiling points. Okay, and so when this says typically has a high melting point, out of these, like covalent molecular, even though like yes, some of them do have like things like estrogen bonding, but relative to the giant molecular mass of the covalent network structures, resulting in these such high London dispersion forces and their high melting points, these ionic structures, which have ionic bonding, and so therefore they're going to have really freaking high melting points. And metallic bonding, same thing. They're going to have those really high melting points. And so covalent molecular structure, they relatively have the least amount of their lowest melting points. And so that does leave us with the metallic bonding for number 10 because they fit all of these. They have a conductor of heat in the solid and liquid states, except their liquid state would be molten. They're insoluble in water because they're not polar, and they do have a high melting point.